All right, so we're going to start limits. Limits are something that we're going to focus heavily on in calculus. So these next videos, it's really important that you at least get an exposure to this stuff. I don't expect you to have it locked in and memorized, especially, just doing it through a video. But next year, for those of you that are planning on taking calculus next year, whether it's at Corona High or whether you're a senior, you're going off to college next year and you may end up taking calculus at some point there, limits are a big thing. They're the foundation of calculus. So this is an extremely important next set of videos. First, I just want to go over something that I know you know, but you're going to confuse with limits. And so limits happen with a function. So I'm going to throw in a function here, just a good old standard, simple, easy linear function, f of x equals 3x minus 2. Okay? Nothing too crazy about that. If I asked you to find the y value when x is equal to 5, I could write that all out in words. Find the y value when x is equal to 5, but that's a lot to write. Instead, in math, we can just do this. Right? That says the same thing. What is the y value when x is 5? And the way we evaluate that is we simply take the 5 and we plug it in, right? This is nothing new. We shouldn't have any issues with this. So we just do 3 times 5, which is 15, minus 2, which is 13, and 13 is the answer. Now we have to be very careful with this idea. This idea is evaluating the y value at 5, which is going to be very similar to what we do with limits, but limits are not the same thing. We need the definition of what a limit is, and there are a couple of different definitions. The definition that we're going to be looking at is not the actual real math calculus definition of a limit, but it's one that fits. It's a good enough definition for us, so let's go ahead and get that up here. And so, poof, by waving my magic lightsaber, I wouldn't carry a wand. I mean, Harry Potter's fine, but it's Star Wars Day when I'm recording this, so I gotta wave my lightsaber. If f of x becomes arbitrarily close to a unique number L as x approaches c from either side, then the limit of f of x as x approaches c is L, and this is written in this fashion. That is a very important setup. This is something that you're going to be looking at a bunch, as I said, when we get to calculus. The way that we read this last sentence here, this math sentence, we would read that as such. The limit, hence LIM, the limit, and then underneath the limit it says x with an arrow c. What that means is the limit as x approaches c. Now c is just a number. So the limit as x approaches 9, the limit as x approaches -4, the limit as x approaches 0. Okay? So the limit as x approaches c of our function is f of x. So the limit as x approaches c of f of x. Let's say f of x was x squared. We could put x squared there, and then we would write the limit as x approaches c of x squared. Okay? And then it equals L, and so we would just say is L. Now, L is also a number, okay? So L is a number, and C is a number as well, okay? It can be really basic, and a lot of times, as we're going to find out, the y value at C is a lot of times what the limit is, but it doesn't have to be. And so this is why we went through this f of x, f of 5 thing. F of 5 is 13. What that means is the y value when x is 5 is 13. We are not going to be finding y values. We know how to find y values. We just plug it in. We're going to be finding the limit. So the example that we're going to look at looks like this. We're going to look at, just as it's written over there in the definition, the limit as x approaches 5 of our function f of x, which I'm going to write out the function 3x minus 2. This is what we're trying to evaluate. It's important that you look at all of these pieces and see what they are. This limit x approaches 5, that thing right there, that's an operation just like a square root sign. I know it's got words in it, but you have to, it is an operation. It's like a plus sign. That sign right there, limit x approaches 5, has the same properties, is an operation, just like this minus sign is an operation. Just like there's a time sign in between the 3 and the x, that's an operation. The limit as x approaches 5 is an operation, and it's important that you understand that. A lot of students don't. A lot of students will do work and they won't write that all the time. It would be like doing a square root problem and never writing the square root. If you don't write the square root symbol, how do you know you're taking the square root? We write this here until we're evaluating it, and we'll see how we evaluate it. Now, to do this, there's a shorter way to do this, but we need to build to that shorter way. The way that we find a limit, if we read the definition again, the definition says the limit, if f of x becomes arbitrarily close to a unique number L as x approaches c from either side. So we're looking at f of x becoming arbitrarily close. Okay, that means is we have to look for patterns. We don't care what the y value is when x ends up equaling c, or in this case, we don't care that the y value when x is 5 is 13. That means absolutely nothing to us right now. It may end up meaning something later, but for now it means nothing to us, not when we're trying to do this example. What we're going to do is we're going to create a table, and oftentimes you're going to want to use your calculator just because it goes faster. So what I'm going to do is I'm going to make an XY table just like you did way back in the day when you first started to graph things back in Integrated Math 1. We made a little table of values, we picked x's, we plugged them in, and then we plotted the dots, right? Hopefully you remember doing that. This time around you're not plotting anything, but that table still has a lot of value to it. So what I'm going to do is I want to get really close to the number 5. Now, I can start this at any spot that I want. I could start all the way at 0 and count up. 0, 1, 2, 3, 4, 5. I could start at any number that I want to, but I want to get really close to 5. So I'm looking at increasing my values here, changing them on an order of 0.01. That puts me pretty close to 5 to start with. Oop, that should be a 0. That puts me pretty close to 5 to start with. My table starts with 4.97. That's already really close to 5. Do I have to start there? No, and that's what confuses a lot of students a lot of times. They get hung up on where should I be starting. It really doesn't matter, but you want to be really close to 5. I think 300ths, 4.97, is really close to 5. Maybe you want to be closer, and maybe you start your table at 4.999997, and then go 4.9998, 4.9999. That's fine. It doesn't matter how you start your table. I typically go by hundredths, because hundredths are close enough. You'll tend to see what's going on with those hundredths. Now what I'm going to do is I'm going to take 4.97, 4.98, 4.99, etc., and I'm going to plug them into this function 3x minus 2 and just get their values. Now I've already done this because, I plan my notes. And so let's get those y values in there. All right, so I waved my magic wand and I put those y values in there. Poof, there we go. Notice I did not put a y value at 5. I know what the y value is at 5, and I could figure that out, and that will come into play later. But when I'm making my table, I do not care about what happens at 5. That's the most confusing thing for students. A lot of times what happens at 5 is cool and is going to be our answer, but sometimes it isn't. And so because sometimes that's not what our answer is going to be, we ignore what happens at 5 because that's not what this question is asking me. This question does not say what happens at 5. In a sense, what this question is asking me is, what does the y value get close to as x gets close to 5? That close to phrase is extremely important. If I just want to know what's the y value at 5, I'll just do this, and there's no point in this lesson. So that's not what we're doing. It's very, very important that you understand this idea. It's not about what's happening here at 5. It's all about the pattern both before 5 and after 5. Now, I don't want to go 1, 2, 3, 4, 5, and then 6, 7, 8, 9. Those gaps are too big. It can be very difficult to spot the pattern. It might not be. For us, it's going to be super easy to find these patterns, but we're going to look at it on a very, very small scale. That's why I started at 4.97. In my table, I'm only traveling from 4.97 to 5.03, so, I'm only changing by 0.06. That's not a big change, right? And so that's why we're looking at these very, very small numbers instead of increasing by ones or something like that. Now, when we look at this, we just look at the pattern, and we have to look at the pattern in both directions. We have to look at the pattern of these three numbers and see if there's any pattern, and look at these three numbers reading backwards from the bottom of the list and see if there's a pattern. This pattern has to be the same. If there are patterns and they're different, we'll get to what happens with that. For us, for right now, they're going to be the same. And so when we look at the pattern, and you could do as many as you need. I did 4.97, 4.98, 4.99, which gives me 3 values. And after 3 values, I'm pretty confident I can find a pattern. You might need 4 or 5 or 6. So maybe you start at 4.92, 4.93, 4.94. Whatever you need to find the pattern. You can't just start at 4.99. There's no pattern for you to determine. You can't just go 4.98 and 4.99 because that pattern, just looking at 2 numbers, we could infer a lot of different patterns only looking at 2 numbers. We want to look at more than just 2 numbers. That's why I have 3 here, 12.91, 12.94, 12.97. That way I can see the pattern, and I can see it over at least 2 examples instead of just looking at the pattern over 1 example, right? The more examples you have, the better. So really going all the way back to 4.95 or maybe even 4.90 and looking at a full pattern would be better. But because I know how this is going to work, as long as you got 3, you're good. So you should have 3 numbers in either direction of whatever you're limiting. If my limit was, say, the limit as x approaches 1, then I would want 3 numbers before 1, 0.97, 0.98, 0.99, and 3 numbers after 1, 1.01, 1.02, 1.03. Okay? So, looking at the pattern as I increase towards 5, I look at 12.91, 12.94, 12.97. Hopefully we can see that that pattern is changing by 0.03, right? The change, that delta means change, is 0.03 for this side. So if I infer that pattern even further and keep that pattern going, that would tell me 12.97 plus that 0.03, that would tell me, let me put it right on the space, that would tell me the y value here should be 13 according to that pattern. However, I can't just look at the pattern counting up, I also have to look at the pattern counting down. So when I look at 13.09, 13.06, 13.03, I see that pattern as well, and hopefully that pattern's pretty obvious. That change, delta means change, that change, it's going down by 0.03, and so if I keep that pattern going, that would tell me if I follow that pattern that that number would also be 13. That's a good thing that they're both the same. Since they're both the same, then I can come up here and say I have now figured out what the limit is. The limit as x approaches 5 of 3x minus 2 is 13. Now the reasoning is the most important part. It's not 13 because f of 5 happens to be 13. This and this are the same. Kind of coincidence. It's not fully a coincidence, but they don't have to be the same. Those 2 things are asking 2 very, very, very different questions. This one up here, I'll circle it in purple. This one up here is asking you what is the y value when x is 5. This one down here is not asking you that. This limit is asking you, what does the y value get close to when x gets close to 5? I know it sounds like the same question, but they are distinctively different. They happen to have the same answer in this case, but in the next video, we're going to look at a bunch of other examples, and we're going to see that it's not necessarily always going to be that value. So, we'll look through that next video. That's where we're really going to get into a bunch of different examples and really drive this point home. It seems pretty easy here, but it is going to get confusing and complicated. Not more so than you can handle, but it's not going to be just as easy as plugging in the number and getting 13. So look for that video, and until next time, stay safe and stay healthy.